Okay, let's try this out. So today we're going to talk about electric current and connect that to what we call the electron current and the electron drift speed. So let's go ahead and throw some stuff out. So we've mentioned before, I think, that electric current which we'll give capital I for its label, is the time rate of change of electric charge at a fixed location. And that's governed by the equation I equals dq dt. So an electric current then gets to have units of coulombs per second, which are amperes or amps. And they have the symbol capital A. Okay. So let's see. So the current then gets carried through solid state objects, through metals, chiefly through electrons. Current can flow through the motion of ions as well, through other charged particles, be they positive or negatively charged. But the primary charge carrier in solids, in metals, such as in our wires, is going to be the electrons. They're the lowest mass component. They are going to therefore be accelerated more by the electric field than protons, which would experience the same force but are about 1,800 times more massive. So less motion. So all of our electrons then, all of our metals then, we are familiar with the idea that metals are composed of all of their atoms, where they're bound to each other through the electrical attraction of the positive nuclei and inner shells of electrons, with the negatively charged sea of electrons, about 1 electron per atom, more or less, is more freely roaming about the entire metal and is able to hold it together, gives it its various properties, like the ease of conduction of electricity through the motion of those electrons, ease of conduction of thermal energy as well, through the same thing, and gives it properties like malleability and ductility, because the whole structure can be attracted and held together by this distributed collection of charges, while still being able to shift around a bit. Anyway, so we're going to express this idea of electric current and motion of charge in general, first by taking a look at the motion of the individual charges, the electrons in this case. So we're going to define another quantity here, lowercase I sub e, which we'll call the electron current. And that gets to be the rate at which the electrons are passing through a particular location, a fixed location, with respect to time. So how many electrons pass through a point at a given instant, or a given rate of time, at a given rate of time. And the electrons don't move in a continual fashion. You may expect that if you have this chunk of wire that I've blown up here, all these red bits here are supposed to indicate the positively charged nuclei and inner parts of the atoms, the more or less stationary parts of the metal. The electrons in our sea of electrons, we impose an electric field across the thing. Let's say that our field gets to go this way towards me, towards your left. Then the electrons, absent other charges, are going to accelerate along the way. But they don't wind up accelerating. Well, they do, but on average, not so much, because there's all these other positive charge stuff in the middle. And so what they do is they're going to bang around all over the place. They're going to keep encountering these positively charged nuclei and bouncing off of them hither and yon. However, because we have this electric field imposed on the situation, they don't just move around randomly like we would from thermal oscillations, just kind of vibrating around, more or less focused on a particular zone. But they do accelerate. They're negatively charged here, so opposite the direction of the field. That acceleration is leveled out, but they do get a net motion, a net more or less constant speed, which we'll call the drift speed. Since it's not the speed of any given electron at any given time, but rather it's the average speed of any individual electron, or the average speed of the electrons, the average speed of the electrons through that over time and across the various electrons. So we'll call that V subscript D is our drift speed. And that gets to be our average speed of the electrons. How well does that show? Let's get you in the shade for a moment. A little bit. Okay. So, what we're going to do, though, we want to be able to express eventually our electric current in terms of our speed of electrons, and that in terms of the electron current. So how do we put this all together? And in terms of the dimensions and other properties of our current carrying object. So we'll throw out a few other definitions here before we throw the algebra up. We're also, go ahead and let's put that there. We're also going to define capital N sub E. Capital N is always about a raw number count. So this is the total number of electrons that we're talking about. And we're using this in our definition of electron current. So number of electrons passing through a location per unit time, that's going to be our electron current. So I'll go ahead and stick that down there. Electron current then gets to equal that number of electrons over delta T. And you may be thinking, oh, well, we're doing calculus, why isn't that a dn dt sort of thing? Well, this is all talking about the bulk motion of like moles of electrons. So we're really talking about averages here, and the differential relationships are not, it's not as necessary to go there for this. So that's that, and that's just sort of definitions here. And then meanwhile, this drift speed here, that's the length that the electrons move per unit time as well. Again, it's another average because we're talking about bulk motion here. So we can deal with like averages over time. And then finally, we want to talk about, we want to define another term here, and that's number density of electrons. And that we're using lowercase n with a e subscript. And number density is number per unit volume, amount per volume. So like 10 to the 28 per cubic meter, 10 to the 28 electrons per cubic meter, that sort of thing. So that will get its own equation as well. So that's the number of electrons per unit volume. I'm writing out VOL there just so that we don't confuse it with potential. Okay, so those are sort of all our base terms here. And I'm going to clear the board and we'll throw some algebra in here and connect them together a little bit more. Okay, so let's remember what we found already. We've got electron current is electrons per amount of time passing through, divided by the time it takes to for them to pass through. We have drift velocity of those electrons is, here, let's color code these. Drift velocity is just the distance those electrons move per unit time on average. And number density of the electrons is number of electrons per unit volume. And then here I'll go ahead and just stick it as V here. Capital V gets to equal volume. And if we have a cylindrical wire here, that volume then gets to be that cross-sectional area A times that change in position. Go ahead and stick that over here. A is our cross-sectional area for our wire. Okay, so we have all these lovely things. And we can go ahead then and say, all right, we want to get electron current. So electron current, if that's number of electrons per unit time, and number of electrons is electron density times volume, then our electric current gets to be electron density times volume divided by the time it takes for those to travel. And then that in turn winds up being the same thing as the electron number density times that cross-sectional area times the distance that they're traveling divided by the time it takes to do that traveling. And then we had defined the drift speed as that change in position over change in time. So then that makes it so we can relate our electron current to that drift speed. And now we have a useful relationship between electrons per second and meters per second for those electrons based on how many of them are around and how fat of a pipe, how big of a cross-sectional area we've got to shove them through. So let's stop there, and we'll pick this up in a moment.